What you're seeing here is a periodic solution to the three-body problem. You can think of the dots as maybe planets or stars flying around space, being affected by the gravity of the other two bodies. This system is driven by a set of differential equations that I'm simulating in Python using my own numeric solver. And today I want to take a look at how solvers like this work under the hood by throwing all sorts of hard physics problems at them. So join me on this small visit into the world of numerical simulations. Pretty much anything in physics that has to do with motion in one way or the other is governed by a differential equation. Unlike regular equations, where we for example want to solve for x, differential equations are in terms of a function and its derivatives. If y would describe some position, then y dot would be the velocity, and y double dot the acceleration. What makes these equations special is that once we solve them, they allow for physical input. The equation above will always give us x equals -1/4, no matter what we do with it. But if I want to describe, say, these springs here, I want the right one to jiggle more if I give it a greater push than the left one. This push would be a boundary condition, and the variables a and b in the solution of the differential equation can be set accordingly. To see what I mean, let's stick with our spring here. We can actually derive its differential equation with Newton's second law of motion, F equals ma. The acceleration, so y double dot, is equal to the sum of forces, which for a spring is just a linear restoring force. For simplicity, we'll ignore this damping term right here, so we'll expect our spring to bounce around infinitely. To get this spring to move, I set up this simple visualizer with the Manim library. What determines the position of the mass at the end are the entries in this array of y values. Right now it's empty, so if we run the simulation, the spring doesn't move. But if you remember, our differential equation told us that the current acceleration is given by k over m times the position y. So every iteration, let's set this acceleration value. The acceleration, in turn, affects our velocity. It gets incremented by our current acceleration, multiplied by a very small time step. The same happens with the position. Our mass moves by however much its current velocity is, times the time step. If we run this now, we indeed see our expected wiggling motion of the spring. Obviously, this is only an approximation of the true behavior. The smaller our time step is, the more accurate our simulation is going to be. We can also bring back the damping effect by adding this term that reduces our acceleration based on our current velocity. And now, after a while, our spring runs out of energy and stops. But simulating it is not the only way of getting the motion of the spring. Alternatively, we can also just solve the differential equation. For a simple equation like this, we can almost guess the solution entirely. We are looking for a function whose second derivative is equal to itself times a negative factor. So good candidates for that would be a sine or cosine function. And if we differentiate twice, we see that they both satisfy our equation, as long as we choose omega squared to be k over m. So wait, if we can just solve differential equations like that, and get an exact solution, why bother simulating them? To explain, let's take a look at this system here. Now we have coupled springs, so the blue mass is hanging on the red mass. If we want to simulate this system, we don't need to change too much. we introduce this second spring system with its respective coordinate and make it so that the acceleration of the masses now depends on both positions according to Hooke's law. And just like that, we have the correct motion of the springs. Fair to say, it's already a bit more complicated than a singular spring, even without the dampening. And here you can see me solving the system by hand. Even though I already know what the result should be, it still takes me a fair bit. And all in all, this is still a pretty simple system. In general, we can encounter much more complicated ones. Now, complexity wouldn't even be our main issue. Yes, solving the equation takes some time, but even with all the theorems, methods, and everything we know about them, some systems are still straight up unsolvable. Proving the existence of a smooth solution to the Navier-Stokes equations is one of the Millennium Prize problems valued at $1 million. So as our system gets more and more complex, we'll have to resort to simulations sooner or later. My original goal was to get as far as simulating the Schrödinger equation and maybe some fun heat dissipations. But as I kept working on this video, it just got longer and longer. So instead, I decided to split it up into two parts, where today we cover the ordinary differential equations and deal with all the partial stuff in the next video. We'll start by taking a look at the simplest family of differential equations there is. Initial value problems. IVPs are differential equations of the type dy dt equals some function f of t and y. Say we're interested in the position of some object, and all we're given is its velocity and its initial position at, say, time t equals 1. To help with visualization, I'll draw the correct solution right here. But for now, all we know is this initial point. If you had some calculus, you know that the first derivative of a function gives us its slope at some point. And the slope is a pretty good estimate of the function values in the immediate surrounding of the point. So to find the next point of our function, we will just walk along the slope for a small time step dt. And where we land is the next point. We do this again from this new point. And again, and again. We're not completely off with our estimate, but the time step is still too big for this idea to work. So watch what happens as I decrease the time step. This already looks a lot more accurate. And in theory, we can push this time step as small as we want, at the cost of more computation time. Now, in this example, we've only looked at derivatives that don't have a y dependency. If we also allow for that, we would have this 3D graph that also takes in our current position to give us the slope. But since this function is known, we really don't have to worry about it too much. This approach of going along the tangent is known as Euler's method. We start with our given initial point and calculate the next point by adding this tangential offset to our current point. Then we repeat this for the next point and the next until we've reached the end time. Let's test our algorithm on our spring system. Unfortunately, most physical systems are second-order differential equations that we can't deal with yet. But because we know the solution, we can artificially reduce the problem to first order just to be able to visualize something. And if we run the code, we get the exact same motion as before. There is actually an interesting system that is first order, the Lorenz Attractor. It's this set of equations that determine the motion of our little dot on the screen. Now, I'll talk a bit more about the shape it produces in a moment. For now, let's take a look at the differential equation. It's a coupled system, meaning that the derivative of each coordinate also depends on the other coordinates. If we're a bit clever about it, we can sum this up in a vector equation. So all we gotta do is update our code to also accept vectorized input. Luckily, with NumPy, much of the syntax can remain the same. So here I'm simulating 2 points that only slightly differ in initial conditions. In the beginning, they're both following the same path. They both orbit the same attraction point and then break through to the other one, but after a while they separate more and more. This makes the Lorenz Attractor a typical chaotic system, where even slight changes produce completely different outcomes. I still think it's pretty cool how such a complex behavior can be described by such a simple differential equation. Now let's move on to second order problems. So the typical physics motion ones, like the spring. Our approach will be to reduce it back to first order, similarly to what I just did before. First, I'll add in another equation where I define dy dt as a new variable v. And with this, we can rewrite the top equation as dv dt equals negative omega squared times y. With this, we just reduced our second order differential equation to a set of first order ones. If instead of calling it v and y, we call them y1 and y2, it's easy to see that we again get the vectorized form. So I implemented this second order ODE solver like this. The main innovation is this part where we generate the reduced function. To showcase this, let's move on from the spring. I think by now we've seen enough masses wiggling around, and instead look at a pendulum. Its motion is dictated by this equation. Alright, I'll set up the solver and give the pendulum an initial deflection of 45 degrees. This is a prime example for an equation that is unsolvable with regular methods because of the sine function in there. After a while, it again grinds to a halt because of this damping term right there. Now again, we can vectorize the second order solver with the help of NumPy. Here the syntax gets a bit more involved, because we also have to generate these secondary equations with the first derivatives. But at the end of the day, it's the same idea as before. This was also about the time I implemented a simple caching functionality. Basically, I have the program note down all the important parameters and store the t and y values. Next time I want to compute a differential equation, I can now check these cache options, and as long as nothing changed, I simply import the values instead of recomputing them. Unfortunately, as is, it can't account for changes in the variable values, since I only compare the bytecode of the functions. so I have to pass them into these cache options here. Now we have all the tools to take a crack at the really hard problems. Let's start with the double pendulum. I'll plug its differential equation into our solver and set some initial conditions. Now, what makes the double pendulum so famous is its chaotic behavior. For this, I'll set up 5 pendulums that are all attached to the same point and give them only slightly varying initial conditions. So, let's see what happens. As you can see, they all started pretty much the same. But after a while, they all desynced and now move completely independent of each other, similar to the dots on the Lorenz Attractor. Before we move on to the 3-body problem, I want to showcase you this special pendulum. As you can see, it's not attached by a wire or a rod, but instead through a spring. This makes its behavior much more complex, but also complicates the differential equation. So far, I've never really shown how exactly you can derive these equations. For most problems, you can find even multiple approaches on Wikipedia. So if you're not interested in the background, that's probably your best bet on finding the equation. But a very elegant way of finding these equations are the Euler-Lagrange equations. They provide a relatively simple approach by just looking at the energy of the system. So using that method, I found the differential equations for this system here. Moving on to the 3-body problem. Here we have 3 objects, for example planets, that all exert their gravitational pull on the other 2. This is one of the famous unsolvable problems in physics. We can easily solve a system of 2 masses, but we still don't have an analytical solution for 3. What I found out during the making of this video is that Blender, a software I use quite a bit, also supports Python scripts. So let's import our coordinates into Blender, turn down the lights a bit, and see them move. This is a more or less random configuration of the 3-body problem, so the masses move around chaotically. There are also periodic stable solutions. Thankfully, I found this video along with the repo of 15 stable solutions, so I was able to simulate them without too much hassle. Link to that is in the description, of course. These 2 are the most beautiful ones in my opinion. Obviously, both have some kind of symmetry that makes them periodic. The outer planet forms pretty much a perfect circle, while the other 2 widely interact with each other. These 2 are a bit more exotic. At least at first glance, I don't really see any symmetry there. I guess that's also something that makes them interesting. Now, I have a bit of a confession to make. The simulations we just watched weren't actually done with our Euler's Method solver. Not because it doesn't work, but because we have straight up better methods. The classical Euler's method is really simple, so I used it to explain the basic idea behind numerically solving differential equations. But the simplicity comes at the cost of accuracy. For more complicated systems, we would need an incredibly small time step to get the desired accuracy. So let's look at some improvements. One of them is, quite fittingly, called the improved Euler's method. Here we rely on 2 points to estimate the next y value. So first we calculate this y half, and use that to then calculate the next point. I have this test function here that we will try to approximate with our methods. Here is our result with the regular Euler's method. As we would expect for such a big time step, the graph isn't the best. But if we plot the improved one, we already get a near perfect result. This idea of adding more steps between calculating the points can be generalized to the Runge-Kudde methods. We can use an arbitrary amount of correcting steps, yielding a more accurate result. Here, for example, I implemented RK4, so a method using 4 points. Now, the improvement isn't that visible in our graph here, but if you look closely towards the last points, you can see that RK4 is closer than the improved Euler. How exactly we calculate these points and why we get a more accurate result is beyond the scope of this video, but suffice to say, we can do a lot better than the Euler's method. Another improvement we can make is step size control. This leads us to the workhorse behind modern IVP solvers, RK45. RK45, or Runge-Kudde 4-5, is a 5-point method that, after each step, estimates the error it makes. And if that error is above a certain threshold, it automatically reduces the step size and recalculates the step. Here you can see it in action. Notice how at this turning point, the points are spaced much closer together than over here, where the graph is flat. This makes this method accurate as well as efficient, so all the animations from before are based on this solver. As I said, I'll have to end the video here. It was a lot of fun to animate and simulate all of these systems, and I'm really happy how they turned out, especially the 3-body problem. In the next video on this topic, we'll explore partial differential equations and dive just a bit into quantum mechanics. In the meantime, I encourage you to try simulating some systems of your own. I've linked the GitHub repo that contains the simulations we've talked about today in the description. I used Manim for the animation, but of course you can use any other library to visualize our differential equations. So thank you very much for watching, and see you in the next video.